Welcome to this explainer on the foundations of iteration, where we're going to explore exactly how to automate repetitive tasks and optimize your clean code architecture. You know, if you've ever caught yourself literally copying and pasting the exact same block of code to process a list of items, yeah, you already know there has to be a better way. Well, today, we're going to master the tools that make that better way possible.
Here's a quick look at our agenda for today. We'll start with the dry principle, move right into definite and indefinite iteration, explore our loop control statements, tackle the dreaded infinite loop hazard, and finally wrap up with resilient loop architecture.
All right, let's kick things off with section 1, the dry principle, or don't repeat yourself. Seriously, why write it twice? Manual repetition is pretty much the ultimate enemy of efficient CPU execution. Think about it. If you have the exact same validation logic, say checking an email format, living in multiple different functions across your app, why risk multiple points of failure? When your project requirements inevitably evolve, having that logic copy-pasted everywhere means you're creating a maintenance nightmare. It's error-prone, it breeds inconsistencies, and it just makes your life harder.
So to enforce this structural programming principle, which we call dry, we lean heavily on loops. Loops allow us to execute a specific block of source code over and over without ever actually duplicating the instructions. It's all about reusable components. You keep your logic centralized in one single place, so if a change needs to happen, boom, it happens right there, just once.
Moving right along to section 2, definite iteration, the workhorse. Now, when you're dealing with predetermined data, the for loop is absolutely your go-to tool. It's the workhorse of definite iteration. We utilize it when the number of iterative cycles is strictly bound to a finite collection. So imagine traversing a list of device logs, scanning a string of characters, or iterating over a database array. You know exactly how many items you're working with right out of the gate.
People often refer to this as a counting loop. It's kind of like playing computer in your head. The loop automatically handles its own internal index tracking, sequentially stepping through everything step by step. If you have an array of 50 elements, it starts at element 1 and marches through every single one until the very last element is reached. And then it just safely terminates. It literally does all the heavy lifting of tracking exactly where you are so you don't have to.
That brings us to section 3, indefinite iteration, the specialist. If we put these two side by side, the fundamental difference is pretty striking. While the for loop relies on predetermined cycles and sequence boundaries, the while loop acts as a specialist. It operates dynamically. It executes continuously as long as a specified logical evaluation remains true. It's entirely event-driven and relies completely on a dynamic state mutation happening inside the block itself.
This brilliantly illustrates the concept of a sentinel loop. Because a while loop is a pretest loop, meaning it actually checks the condition before it runs the code body, it's incredibly vital for things like scrubbing bad data. Let's say you're prompting a user to input the radius of a circle. If they type in a negative number, no way, that doesn't work. The while loop can dynamically reject it and keep asking until a correct positive value is received. That valid input is your sentinel.
Next up, section 4, loop control statements, the arsenal.
To really bend these iterative cycles to your will, we have a specific arsenal of control statements that modify the default flow. First, there's break. You use break to immediately terminate the loop. Like if you're doing a sequential sweep of device logs and you hit a critical anomaly, you just break out of the execution line entirely for safety. Then there's continue. This one skips the remaining operations in the current cycle and forces the loop right back to the top for the next evaluation. It's perfect for skipping over minor warning states. And pass? Well, that's just a syntax placeholder. It performs absolutely no action, but it keeps your architecture structurally sound while you hold space for future logic.
Oh, and Python has this really elegant feature, an else clause that attaches directly to your loops. Here's how it works. If the loop completes all its iterations naturally without ever encountering a break statement, then the else block executes. It provides a wonderfully clean way to handle not found scenarios, like searching through a file for a specific error keyword without cluttering up your code by managing extra flag variables.
Which brings us to the dark side, section 5, the infinite loop hazard, system meltdown.
Look, the danger here is very real. As the dev community accurately points out, a while loop can silently consume all of your computer's available memory.
If your conditional state never actually mutates to false, maybe you just forgot to update your index variable, the loop is going to indefinitely consume maximum CPU clock cycles. That is exactly how you get devastating software freezes and full-on system crashes. Think of it like a faucet left running in a tiny enclosed room. If your infinite loop is constantly appending new data to a list on every single cycle, that data is the water. It silently fills the room until, eventually, the system overflows. You get a massive memory leak and your entire application is brought down.
So to prevent this hazard, you have to strictly implement the 3 golden rules of while loops. Rule 1, always design an exit strategy. Either the condition is guaranteed to become false or a break is triggered. Rule 2, ensure you have a changing variable that actually moves the loop toward its end condition. And rule 3, monitor for unnecessary data growth. You really have to actively manage this stuff.
Let's synthesize all of this in Section 6, Resilient Loop Architecture, Production-Grade Synthesis. Imagine you're building a dynamic API connection retry mechanism. You need to wrap that while loop in safety boundaries. First, implement a max retries threshold. Like, if attempts reach 3, you break. This completely prevents the infinite loop hazard. Next, use exponential backoff. A simple time.sleep command in Python creates a brief pause between cycles, which stops a thundering herd of requests from crashing the network. And finally, ensure your operations are idempotent, meaning you have safe state checks so retries don't cause any unintended destructive side effects. You also absolutely need to be wary of runtime cyclic dependencies, especially if you're working with event-driven systems. Think about it. If event A triggers event B, and B triggers C, and then C fires an event right back to A, well, you've just built an architectural infinite loop. You have to map your dependencies really carefully to make sure your services don't get trapped, triggering each other in an endless runtime cycle. Okay, we've covered the core mechanics of definite and indefinite iteration, unpacked our arsenal of control statements, and looked at the architectural safeguards you need for real production-grade code. You now have the exact weapons needed to conquer manual repetition and avoid those nasty system meltdowns. So here's my challenge to you as you look at your current projects. Where are you still repeating yourself? Find those spots, apply the DRY principle using the loop architectures we've discussed today, and watch your codebase transform. Thanks for joining me for this explainer, and I'll see you in the next one.